own Aziz Kharoof, who will talk about simplicial sets. So in general, feel free to unmute if you have any questions or comments, but please stay muted otherwise. Over to you.
Okay, thank you very much, Q. So today we will talk about simplicial sets. The reason, because our seminar is on infinity category, and almost or most of the infinity category models use simplicial sets. It not have to be, but okay, this is what actually what we will cover here. The models that we will cover in this seminar course, it will use simplicial sets, all of them. But before, actually, simplicial sets is like a combinatorial way to describe topological spaces and to study homotopy theory. Okay, so let me write this. Simplicial sets. Okay, combinatorial. Historical way to describe topological spaces and of course to build homotopy construction or to study homotopy theory. Of course, it's started actually, this simplicial, what I know that it started from classifying space, like describe classifying space of a group. But we will do this during this talk. And of course, we will give a hint why it's good for to describe infinity category, okay? Okay, let's start something before, something that more useful and more known for people is a simplicial complex. Simplicial complex. Okay, what is simplicial complex? It's actually some vertex, like I have V, it's subset of vertex. X1, X2, Xn. It can be infinite, okay, but let's say that it's finite set of vertices, and we have some subset of this V, some subset that describe actually point if it's just one. If this two, like x1, x3, something like this, it will be segment like, okay, it will be, if this is 3, it's a triangle like this, but we need actually to glue them through simplex also. Okay, this is one simplex, this one is 0 simplex, and so on. Okay, like pyramid, it's 3 simplex like this, but we need to glue them through simplexes also. So a simplicial complex is a set of subset, okay, set of subsets of V, the rule such that we cover V. Okay, let's say we cover V because we want this to be our vertices. We cover V, and if let's say sigma 1, sigma 2 is in V, and this is inside this, sorry, if sigma 2 inside and this inside this, then sigma 1 also inside is in sigma, sorry. If I have to simplex, so the sub one will be also simplex. Okay, this will see the instruction also will be like this. So this will be also inside this sigma. Okay, all of you, I'm sure that know this simplicial complex. Okay, the geometric realization of this we can see like okay, something like this. I have a triangle. I have maybe one simplex. Maybe here this one. Here there is some pyramid. Okay, something like this. Yeah, but it's not have to be connected. Something like this. Here is the vertices. Here is how it's glued to each other. But of course, it's not every topological space we can describe in this way, in this combinatorial way. You see here, we didn't mention topology. We just have some point combinatoric, like, okay, right, just point. This is what we want to do, but still not every topological space it's look like this, or at least like homotopic to this or something like this. So let's now go to something more. First of all, a map between simplicial complexes, you know how it's mapped between. So a map, like, let me, before we go, because I need this later. So a map between two simplicial complex, a map. In this category of simplicial complex, it is a map between the vertices. It's a map actually between the vertices, such that if I have a sigma in here, in sigma, then f of this, if I apply f on all these vertices and build this, I will get also simplex there, okay? This is a map between vertices. Now, to do this more, now I want to do this more flexible and more abstract. We can do the following. We can put all the one simplex in some, but this when we have order, we need the order. Like if I have the order on the, if there is an order in the vertices, so we can do this, or we can describe the simplicial complex like this simplicial complex sigma as the following. I put here in sigma 0, I put the vertices. Yeah. And then in sigma 1, I put all the one simplexes, okay? The one simplexes. And so on. In sigma 2, the second order simplexes, and so on. And I have a way to describe here. I need two maps to describe the relation between this one simplexes and their like edges, okay, like this is simplex, okay, but there is 2 points here, right? So I can describe this by two maps here. I can call this D0, D1, but here I have order, okay? So I know that there is order because there is order on the vertices. So if I have one simplex like this, so I have order, I can know what is D0 of this. I mean, when we remove those, so, okay, from 0 to 1, when we remove this, so it will be this. D1, if I apply the function D1 in one simplex here, so it will give me this vertex, okay? The same if I have triangle, and also we have order here because we have order on the vertices. So we have here three maps, actually, three maps from here to here, right? We have three maps. We have the okay, if I have an order, so it's easy to describe this map like D. If I apply D2 because it's okay, this is like we can convert that this, or we can have agreement that this our rule that D2 is this one. Let's give me this one here, because here we have all the one simplex, so I need here D0 and D1 that give me, oh no, this is D0, give me this one, okay, and there is another one here, another, if I apply D1, it's give me this one, okay, so I need here 3 maps to describe. Also, I can describe by composing between these maps, I can describe the vertices of this, right? Yeah, and so on. So on, if we continue above, we need more, like every time we need, like in the pyramid, there is 4, which is 3 simplex, there is 4 2 simplex as it faces, right? We can describe in this way. Now, so this way it's more flexible because we can generalize now this and define, we can define, let's go definition. Actually, it's called semi-simplicial set. This thing is called semi-simplicial set, or delta complex also, there's another, okay, semi-simplicial set X is a collection of sets X0, X1, X2, and so on, with what we can call this faces map, right? Faces maps. Faces of face maps, sorry. Face maps. That give me the faces from every xn to xm minus 1. Okay, how many we have from here to here? We have d0 from, we say from d0 until dn here we have, right? We have these maps. And of course, there is some connection between this map. Actually, like let's take for example pyramid. If we have some pyramid, and if we want to go like, okay, this is 0, 1, 2, 3. If we want to go to this one, so I need to apply 2 faces map, right? Like this is a pyramid. Let's call the pyramid X. This pyramid. Okay, sorry. Let's call this pyramid X. And if I want to go to this, so I can apply first of all D0 on X, right? And then I will go to this triangle. So in this triangle, you know the order, right? The order, there is order of the, okay. This is the order. Yeah. So D0, sorry, of X, and then I apply what is this will be? This will be the first one. Like, yeah, in this triangle, this is so D0 on this again, right? D0 and X and D0. It's a good example because I want something to be, okay, no problem. D0, oh, let's take maybe this will, okay, no problem. Let's continue. But we can do this in another way. I can take D1, D1 of this, of the pyramid, right? And then in this, I will be here. So again, it's D0 of this triangle. So actually, we have this rule, like in general. So the rule will be, it's here. So this will be the rule, such that, so we add this in the definition. I just give here some example, but let's add this in the definition such that we have rule between these faces maps. The rule is like this: di dj is equal to bj minus 1 di when yeah, here for example. So every order simplicial complex we can see in this way, in this abstract way, but this definition actually have more examples. Like here, we can talk about something like this. Another example of, okay, here example of the degeneracy map, but if I want to give example of this semi-simplicial, I can give like this example. That here we have in x1, I have just one x, and x2 is empty, everything is empty above. Okay. And here in x0, I have just 1 point. So it's obvious what the d0 and d1 doing here. Okay, send this to the point. So this actually present for us, like I have just one segment that have d0 and d1 is the same, so it's a circle. But we see that in the in a simplicial complex, this is not simplicial complex, right? This is not, we can't describe this in the language of simplicial complex. So we see that we are more flexible here. And of course, more abstract. We just say that our, like, it's like a diagram. What we have actually here, we have some diagram in sets, actually, simply. So let's maybe say this, like semi-simplicial set is actually a functor, some functor from some I to set, like this is the shape of the diagram. This give me the shape. So the shape of the diagram, it's like this, like we have here 0, 1, 2, right? This is 3, and we have here 2 maps. Here we have 3 maps. Here we have 4 maps, right? Is a functor here. And with some relation between this map. Okay, we will describe what is, okay, the relation is this, like it's coming from something like this, not exactly this. We will describe it later when we talk about simplicial sets, not just really, but okay, let's say this, like we have such a diagram like this. This is I, and we have such a functor like this, because why I'm saying this, because now it's easy to describe what is the maps between semi-simplicial. What is maps between two semi-simplicial sets? What is a map? Like a map between, if the object is a functor, so the map is a natural transformation between them. Yeah, right. Between. Because we lose the way to describe map like this, like what we described before, like it's something like this, that, yeah, we lose this way. So we have now this way to describe this simplicial sets x and y is a natural map. And it can easily describe, if one not notice this and he want to describe a map, he will say, oh, okay, it's easy, like, okay, it's, I have this, it's just a map everywhere, like from one map from this set of n simplex to n simplex, and map from n-1 simplex to n-1 simplex, but just it's preserves the faces. Like if I have something here and go to some face here, and I send this to some n simplex y, so it's this one have to go to the face of y, right? This face of y. So it's like that makes this diagram commute. This is exactly to say that it's natural map. Okay, this is the same to say that it's natural. Okay, so this we have, we try to abstract our definition of, like, started from the simplicial complex, which is a combinatorial way to describe some topological space, but we want to make it more flexible and more abstract. Then we got this, but there is a problem on this, actually the problem on the map. What is the problem on the map? That it's not covered important map like that we have between topological spaces or between simplicial complexes. Like simplicial complexes have more maps. Now let's look at this map, the easy map in simplicial complex from segment to a point. Like that, there is unique map. Okay, what is this map? This map that sends this 0, 1 to 0. Okay, this. Okay, this map we can describe here. We can't describe. We can catch like in the category of semi-simplicial. Simplicial sets. We can describe this. So why? Because okay, we just allow us to send simplex to a simplex, right? We see it's like we can just, sorry. We here, like if I am here, x1, so, and this is y, like what is y? It's just, what represents this? Represents this is just one point here, like this point, and that is, but I don't have any maps here that send anything here, like I have some segment here in x1, this one, okay, so we don't have a map to this, right? So we don't have this map. In order to fix this, actually we need to add, because what happened here, like let's say, like there is a map from here to here, right? Like we need to define it to be like we can map from here to here. But actually, instead of doing this, let's put some representative to this here. Why we can do? Because every point we can look at this as the edge, right? Every point we can, like we all of us know, like we have a question maybe in the school, and suddenly there is a circle and the point described as a circle. Okay, we say why described as a circle because the radius is 0. Like, okay, you can't see a point as a circle, as this, like what it's called, ball. Like, yeah, you can see a point because the same we can see actually, but here in many ways, because here in one way, in this one we can say in one way, like I can see as one edge by, like I imagine things like this. Like also I can see edge as a triangle, but in two ways now. I can see, because I can, like this is 0, 1, I can add another 0 here. And like repeat this one, this segment here, repeat, and this, but actually it's the same as this. It's just, I imagine this to be a triangle. I can do this. There is another way, of course, like this, to add here 1. Okay, so this will be like this, right? Yeah. 0, 1, we repeat this all the time. So this one, or this one, I can add here 1 and then 0, 1, repeat. Yeah. So we repeated this many times here, many times. So actually we have just this 0, 1. There is two ways to do this. For points, there is one way to do this actually, to repeat this point. And to look at this point as an edge, and then I can do this and send this one here to this. Actually, this will represent for me, this we can do in not in semi-simplicial. We have to improve this category. We will see by adding this what's called degeneracy maps. Okay, we will talk about this. But if we have this, when we can represent this map. Okay. Okay, so this is the idea of degeneracy map. So like we have from x1, from x0 to x1, one like this degeneracy map, as we say, by just repeating this point. Like this is abstract. This is what, but okay, we imagine this like this. This is what happened, and we will see. We can describe this by the relation between things. We will see. So, and we have from here to here S0, S1, we have 2, and one can imagine that to like triangle in how many ways I can see it as a pyramid in 3 ways, like by repeating every one of the vertices. Okay, so S0, S1, S2. So okay, let me now define what is simplicial set. So definition. Simplicial set is collection of sets x0, x1, so on, with face maps. We still with face maps. Just we improve ourselves. We added this degeneracy map. So we face maps. We still have this. Like I still have. Sorry. Again, from xn to xn minus 1, we have di such as I from 0 to n. And these maps, degeneracy maps, now it's going above, like this is imagination maps, like we want to think about n simplex as n the plus 1 simplex, and we can continue, like we can continue. There is another from every, we can compose like degeneracy map, and going from, we can think about even point as a pyramid or as more bigger than this. Okay, I going from here from 0 to n also, yeah, from 0 to n. But there is a relation between these such that, so I don't remember this relation, but yeah, I will tell later. We will will tell you where it's come from, all this relation, and how one can remember this relation. So this is what we had before. This is the relation. We have another relation also like this between the degeneracy. Okay. One can easily see this, like if there is maybe one degeneracy, like from x1 to x3, I can do in 2 ways. To x3, I can do by 2 ways through x2. Okay. So this is what this relation tells us. What we described for face is the same here. And the other thing is the relation between degeneracy and faces. Actually, is what is the faces of degeneracy? This, okay, sorry, this if j bigger than I, and if j equal to I, oh, okay, I don't have to say this, I can say this in this way, the jj or dj plus 1 sj, this will be the identity. Why this actually? Why this? We already see this actually here in the triangle. We see that when we did this degeneracy, like this is degeneracy for this one. So we see this, that there is two places, two faces here that have the same x, like it's identity. Okay, if we now take this face, so we back to this, the same here. And for the pyramid, for more higher order simplexes, we will see that there is just 2 places that we repeat if we take the faces, it's give me the original simplex. Okay, and if bigger than g plus 1, then we have this. Okay. I hope it's obvious. Okay, there is composition here. Okay. I hope it's obvious now what we mean by this. Okay. So now another way to describe this and to remember this kind. First of all, is there any question? It's okay. Can I continue? Okay. Another way to describe this, because we see again, it's also functor. Like simplicial sets is a functor because we have some diagram here, but now not this diagram where I put here. Now I have another maps here, one maps here, two maps here, three maps, right? This is the Dejersey map. So some diagram like this. But where it's come from, this diagram? Actually, it's come from what's called the
sorry, Aziz.
Yes, yes.
There is a question on the chat whether semi-simplicial sets are the same things as delta sets.
Yes, 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 okay. Tamir, it's a delta set. Yeah. Tamir don't have a microphone. He says so. That's why he asked in chat. Yeah, it's the same. It's called also delta sets. Yeah. So simplicial set. Let's describe it another way. But first of all, I want to define the simplex category, like where it's all these simplicial relation or co-simplicial relations come from. But we will describe this. Okay. So definition. The simplex category delta is the following, like object of delta. Delta is this. This is just, this is a simple that I use for this. One, it's 0, 1 set. Okay, this is subset, actually subcategory of the category of sets. Okay. But one, 2, it's 0, 1, 2. This sets. This is the object. And the morphisms is preserving order maps, okay? Preserving order preserving order preserving maps. Yeah. And one can describe now another alternative definition for simplicial sets. Definition for simplicial sets. So it's just to say that simplicial sets is a functor set is a functor from delta opposite to functor x, as we say, from delta opposite to set. Yeah. Why is this actually? Maybe it's obvious that what we have in order of object. Okay, this is what we have actually. We have like x n. It's mean if when I apply on this is this. Yeah, I use this notation before. But in order of maps, we have all the order maps actually that it's generated by these maps actually. Let's see, maybe I have here a place to say this. Actually, we have here all this order preserving map generated by two kinds of maps. The faces maps. The faces maps is this map, like when I have, for example, from 2 to 3, from n to n plus 1, I have this, like I send 0, 1, 2, 3, 0, 1, 2, sorry. Like I ignore one of them. I say I want some preserving order, so I send this to this and 2 to 3. Okay. So this is a preserving. This is called like face map. Actually, this will give me the face, because this is, you see, this functor is contravariant from the delta opposite functor. This means like contravariant functor from where is map from a contravariant. So this will give me the face map. If I applying this on this map, this will give me a map from here to here, which represents the face map. This will represent like this way, like we will send something from x of this, something from x of 3, like in x3, this will be something like pyramid 0, 1, 2, 3. And this will give me the corresponding face map for this, okay? That I'm drawing to, like which one? This one. This will send to this triangle in x2. Yeah. What happened? And there is another kind of map, the collapse maps. We can say that I say here 0, 1, 2, 3. I repeat myself because I want to preserve order. So for example, I send 1 and 2 to 1, and then this to 2. Okay. So this will give me, this will represent, if I apply x, so this will give me x from x2 to x3. This is the way we're thinking, exactly what we did before. This is the way we're thinking about some triangle to be a pyramid by repeating one edge, right? So this is what happened. Maybe one can ask, okay, what about the other map? We don't have in the diagram. You have by composition. You have all, like, where is the diagram? Maybe it's here. Yeah, by composition, like I can get everything, okay? Like going from here to here, maybe composing the jersey and then this map. So actually, the category delta is opposite of this, okay? Is the opposite of this. But then we take the functor to be contravariant, and this will. So this is the cause in this category. Delta, we have some this order map, what I described here. Maybe let's call it some, maybe I will use this later. So let's call maybe this one S1, because it repeats this in 1, and let's call this one D2. Let's ignore the 2, okay? D2 above, like this, okay? So actually we have here also, again, some identity. Like what I wrote here, identities in this category, which calls the co-simplicial identities, and all this simplicial identity come from here. Okay. Okay. So if we define the simplicial sets, the category of simplicial sets, this is the category of simplicial set. Sets, we define it to be the functor from delta opposite to set. And now it's obvious what is the maps between simplicial sets. And we cover this kind of maps, what we didn't cover before in semi-simplicial set or delta complex, delta say, what's it called? Delta complex, I think it's called. Okay, what we call semi-simplicial sets. So we cover this kind of maps. So it's obvious what it's maps between simplicial sets. The map between simplicial sets, again, we can see as the natural maps here between the functors, if we look at this as a functor, or if we want to look at it this way, like it's something which is like here, like it's a map everywhere. map from the n simplex to the n simplex, map from the n-1 simplex to the map, that makes the diagram commute, but also with respect to the degeneracy maps also, not just for the faces maps now, yeah? Okay, let's take some example. The obvious examples that we already mentioned is order, any order simplicial complex, right? We can see this as a simplicial set. And the maps also, we can move to simplicial map, the category of simplicial sets, no problem. Okay, any order simplicial complex. Other example we have here is a standard. It's important, the standard simplex n. So this maybe let me give you how I can describe, for example, delta 3. Actually, this represents a pyramid. What it's have, like it's have a delta 3 in the 0 stage. It's have 0, 1, 2, 3. In the 1, it's have a 0, okay, 0, 1, right? Okay, how I can write this? Maybe let me write, because I already use this notation. No, I use this notation. Yeah, I didn't use with, okay, it's okay, because I use just this with when I have just one to represent it as I said, but it's something else. Okay, so maybe let me, not to confuse, let me use this. Okay, so we have this, like what is this? This is the age that have in one, D0 of this is 1 and D1 is 0. We have, of course, 0, 2, and 0, 3, and yeah. Well, why I do D3? I can do D2. It's easy. Yeah, 1, 2, D2. So it will be faster. Okay, because the same logic is the same. Okay, 0, what we have here, 0, 3, we have no 1, 1, 2. No, yeah, that is. But we have also the degeneracy of this, because every vertex here we can think about this as edge in one way, because we have just one map from here to here is 0. So 1, 1, and 1, 2, 2. Okay. These 3, 2, it will be 0, 1, 2. And the other is degeneracy. Okay, this is the only one. It's non-degeneracy. Let's say what is what non-degeneracy here? This one, this one, this one, this, and the other is degeneracy. Actually, here we can continue. Like I can think about this to be 0, 1, 1 or 0, 0, 1, right? And so on. I can, for example, this again. Like this is even too much degeneracy. It's coming from, it's just a point. It's actually what it's represented, it's just a point. Yeah. And also for above, like the 3n, for n bigger than 2, it's all degeneracies. Degeneracy, I mean degeneracy simplex when it's come from degeneracy, it's Si of something. Or, okay, it's in the image of degeneracy map. Okay, so this is the description of delta 2, and one can imagine how it's delta n in general. Okay. Okay, maybe one can think we added here many things that we don't, but we need it in order to, we see that in order to describe maps between so that's why we need this degeneracy. okay, we will see that we will have another advantage of taking this later. But at least now we see that in order to describe map like this, like degree-wise, the maps to be that makes the diagram commute, this is the way that we can describe many maps, what we want, this degeneracy map or collapsing map, what we say, collapsing map, sorry, that what we showed before. Okay,
hi, Aziz.
so another way, yes.
I have a question. So about the example one, so you are saying that you can see every ordered simplicial complex as a simplicial set.
Yeah.
So the question is, this means also that there is no functor from simplicial complexes to simplicial sets, right?
No, there is. I didn't know before, but actually related to our work, there is no another one. No, there is the nerve, and there is another. Actually, you can do this actually. But take any like sigma, and you take the from here to that. Okay, let's maybe call this f of sigma. This will be simplicial. So what is the n place? In the n place, you take the simplicial complex of, okay? Like in the n place, this will define for you simplicial sets.
Ah, okay.
Okay, yeah, you can do this.
Yeah, because my point was that there is no obvious, it's not like a straightforward that I'm
right, because actually you have
here
to take all the orders, like you have here it's big, it will be big because it's like every order give you something, but yeah, if it's order, it's obvious here.
Okay, thank you.
Yeah, no problem. You're welcome. Okay. Let's continue. So we want, yeah. I want another example. Before I want to say something about this example. I want to say that one can see this example as, but okay, sorry. Just a minute, sorry. Yeah, the other example is the the nerve. I want to move the nerve, but before I move to the nerve, I want to say something that one can see this delta n as a functor, as this functor. Okay. Like this representative functor from where? From delta opposite to set. Okay. Yeah. Well, it will be good exercise to convince yourself that this is what happened. Like this is functor we have. Okay. So let's go now to the nerve. Another example. Nerve of a category, of a small category. Nerve. Small category. Actually, the nerve of small category, let's say that we have C, small category. Like, okay, the object is set, the morphism is set, what I mean, small category. Okay, so we can take the NC0, this will be the object. Here's a set of objects, I can say, the set of, the set of objects of C. NC1 will be the set of morphisms, or C. Okay, here I can write object C. Okay. So, okay, I can write here in C2. In C2, it will be every two composable map in C. NC3, will be every 3 composable. One can imagine how we can continue from here. Okay. And now maybe it's obvious what is the faces map, right? Like if I am here, like the faces maps, it's what is the target and the source and the what is called the co-source. I don't know, yeah, here. And here actually like if I have this here.
Yeah, so that's the target. You were right, source and the target.
The target, yeah. D0 of this is this, G. D1, D2 of this is F. D1 of this is the composition. Okay, and so on. Okay, this is what happens. The degeneracy map is by adding the identity. Okay, like I have here, for example, from here to here, degeneracy map. So there is one way to add the identity here, x of x, and to make it look like there is a sequence of 3 maps, right? Or I can add the identity here, or I can add the identity here. Yeah, it's the same idea what we did before, like something. Okay, it's like if we want to give you this diagram, you will say, okay, what is this? This is just this. What is this identity have to do here, right? Like, okay, so this is a degeneracy map. We have 3 ways like to go from here to here. So this will be simplicial sets. Okay. So observe that this actually it's called the nerve because it's actually depends just on the shape of the category, the shape of the diagram. If we take this category as a diagram, it's not what is inside this topological spaces we talk about, or about groups, or about anything. It's just the shape of the category, right? It depends on just the shape of the category. So another way to describe this one, actually, it's to describe the nerve. It's by the following: nerve of C is actually all the functor from just a minute, all the functor from, sorry, the nerve of Cn, it's a functor from this category to this. We can think about this as a category, actually. Like here, I mean, we can, okay, let me again, like a nerve, it's here, right? What is a nerve? A nerve of C, we see that it's a simplicial set, right? So a simplicial set, what we say, it's a functor from delta opposite to set, right? So I want to describe this as a functor from delta opposite to set. So actually for everyone here, N, I will see this is a functor from N to C. And then one can ask me and say, but this is not a category. But we can say this as a category, actually. We can see this as a category. Like delta, all delta, this delta opposite, like delta, this is a simplex, and there is many ways to describe this. The simplex category, maybe we'll see in another place. Simplex category is category is a category. Like, sorry, this one is a subcategory of the set. Like this is subcategory of the category of set. Like it's have this, or everyone can be a category. Like this one is a category. Like N, I can think about this N as a category, this category. Okay. And this, what we say, preserving order, we can think about this as a functor. Okay. Like this one, for example, from 3 to 2, we can think about this as a functor. It's just a functor that I send 1 and 2 to 1. Okay, so I send this this map to the identity between 1. Okay, we can think about this as a functor. Okay, so that's what makes things that I put here n as okay. What is the functor from this n? So you understand, like it's what is this is the shape of the diagram, like n is the shape of the diagram. So every diagram with this shape. It's exactly what we describe. This is the n simplex in the nerve. Okay. Okay, but here it's easy to see why this description is good, because it's showing that nerve actually is a functor from the world of small categories. Okay, let's call it scat. I mean small categories. Let's call it scat. The nerve, it's a functor from this to this, to here, to simplicial sets. Okay. And this functor actually is fully faithful. We will talk about this next time, but it's good to fully faithful. That means that we can see categories as a category of simplicial sets. And then by asking which kind of simplicial sets is a category, this will be a category here. Which kind of simplicial sets will be category? Which kind of category? There is some some properties of this, the image of the nerve, right here in simplicial sets, and this actually will help us to get two models of infinity category. Because we see, like here is a category, we don't have higher order morphism, but by going to here, we can see a category as something with like imagation higher order morphisms, and then by make the conditions weaker, we can get two models of infinity category. Okay, we will talk about this later. Okay, now let's go to the geometric realization of simplicial sets. We said at the beginning that simplicial sets is combinatorical way to describe topological spaces, right? So how to move it from simplicial sets to topological space? So it's a geometric realization of simplicial set. Actually, given simplicial sets, like okay, we have simplicial sets. How we can see this as a topological space? So actually, every simplex we want to see like n simplex. We want to see as delta n. You know what I mean by delta n. This is the n simplex, the geometric n simplex. Okay, like delta 2, it's a triangle. Delta 3 is a pyramid. So we product this with delta n xn. Like every simplex here, it's delta n. Okay, the union of this. But of course, we have to take the relation between the faces. Like if because here what appear, like for example, I have this one like x some x in x2. So here I product this x with, I take product this x with delta 2. So this represents some triangle. Okay, let's maybe take it as triangle. But for this, we know that D1, for example, of this x, D1 of this, it's also product with delta 1, which is just an edge. But actually, we want to glue this with this, okay? Like this, we don't want to repeat. By taking the union, we repeat ourselves. We want this to be the same as this. Okay. The same if we have degeneracy map, like if we going like this can be also represented by degeneracy of this. Let's take some degeneracy is 0 of this. Okay, is 0 of x, but is 0 of x here will be a pyramid actually. Be some pyramid. Because it's 0 of x, it's in x3. Yeah, so that will be pyramid. But this pyramid actually it's represents this, because actually here we have this map from the collapse map from here to here. Which collapse map? Like if we this 0, 1, 2, this so we have here 0, 0, 1, 2. Okay, so like this triangle repeats itself many times. So we actually identifying this, all of this, like all the triangles that appear. We see that there is many every level we have this triangle until we get this triangle again here, like between here and here, we repeat this triangle. You see, we repeat this triangle along this, yeah. So all of this by this collapsing map to here, collapsing map. This, of course, I will not give a formula for this, but one can imagine this is a formula for this collapsing this as a topological spaces. Like it's depends by these edges. Like I send two edges, these two edges to this, and there is a collapsing map. By this collapsing map, I identifying. Okay, maybe another. This will be codified. Pick another one. So I define this by this collapsing map with all this triangle. Okay. So this is the relation. This is the quotient we do. We can describe, of course, this in another way. As a co-limit, but okay, let's not do this. I think you understand what's going on here. Okay, there is a question because I need to talk about things else. Any question? I say I want to check that. Anything in chat? No, okay, I see now the chat. Yeah. Okay, so this is how we represent the geometric realization. It's obvious, right? It's how we describe in the beginning simplicial sets, the idea. So the geometric realization move us from simplicial sets to topological space. Actually, the functor, we see that's what I built factorial. Okay, it's a functor from this one. We will see functor from simplicial sets to topological spaces. But the things here, what it's give me as a topological space, it's give me good topological space, give me CW complexes. So CW complex, if someone don't know what is CW complex, what we can build as by stages, like I have first of all point, and then I have edges, but I can glue with the point. I have some glue formula how to glue this with the point. Okay, then to this, maybe I glue this with this, I glue, and then I have some disk, and I have a formula how to glue this disk. Maybe I glue all this the faces with the faces of the disk. I have some formula like this, and then maybe I glue this with the points, and I get sphere here. Maybe I glue in here the disk, then I make it contractible. Yeah, like that. Something CW complex, something that I can build. That there is a rule how to build this. Yeah, it's like in the group. Some free group, like something have actually projective group, something that we know how it's built, like everything we know how it's built. Yeah. So the realization of every simplex is if every simplicial set is CW complex. Now we want to define the other direction from topological spaces, how we got the simplicial set. From topology to simplicial set, we have this singular functor. Actually, the singular functor actually is some topological space. Okay, let's call this y because I am already using this. So y will go to sim y. So y in the n place, like the n simplexes, is will be the continuous map from delta n to y. Okay, this is what is this. Okay, one can show that this is really simplicial, give us a simplicial sets, and this is really a functor. What actually important about this two functor that it's adjoint to each other. There is adjunction here. So let's write it. We have this adjunction. If we take simplicial sets x, and here we take the singular y, isomorphic to a map from y, where x is for every x in simplicial set, and y in topological space. So we have here natural isomorphism, actually natural isomorphism. Okay. Now, how to prove this, or how to measure? One can see, like, it will be good exercise if one take a map here and they try to see what happened, how it can look at the map here. But actually, it's easy here to see why it's right for why these things, it's right for these ones, like for delta n. Because actually for this, what is this? Like map from delta n to singular, actually to anything, it's give us this one. Why is this? Actually, one can see this because of the unida lemma, because we already described this as a delta n, and then we have to put this in here in singular n. This exactly give me this, and it's easy also to see that this is the only one, like this n is the sorry, here there is someone that generated everything, that by if I have the image of this, I know everything. So it's just one n simplex. Every one n simplex here give me a map from here to here. And this actually is the definition of this is a topological space from delta n to y, but this is exactly actually the realization of delta n. Okay, it's easy to see this in terms of the n simplex, n standard simplex, but actually there is a fact that every simplicial sets we can describe, like what we did the realization, something like this, we can describe as a co-limit of n standard simplexes. Okay, like for every simplex in the simplicial sets, we take standard one and build a diagram like this, and then the maps between the diagrams from the degeneracy and the faces maps and the co-limit of this. And if one can move from here to prove that it's correct for every one of x, because one can take now simplicial sets of this co-limit, what I described of something like delta n, like this. Okay, delta n can be anything like delta nx for every x in any xn in any degree. Okay, some co-limit like this, and by using this, the co-limit will be limit outside, and by using this and moving to this, he will see that we will get the realization. So it's easy from here to move to prove this in general. Okay. Okay, but actually this adjunction, it tells us more about this connection between this category. It tells us connection between the category, how this singular and realization connect between the category of topological space and simplicial sets. It tells us more, actually, this is a Quillen adjunction. This is Quillen adjunction. Okay, we will talk about this later when we talk about model category or things like this. Even it's a Quillen equivalence. Quillen, yeah, it's Quillen like this. No, sorry. Yeah, sorry. Quillen equivalence. What it's mean here that if I have here a map from here, every map we can represent as a map, we can see as a map here, right? So if I have a map here, and I can represent a map here, so this map, this in topological spaces, this in simplicial set. So this map will be weak equivalence, or this, maybe we know what is weak equivalence in terms of if and only if this weak equivalence. Actually, we didn't define weak equivalence, we maybe will define later, but actually this is the reason why people sometimes say, okay, topological space or simplicial sense. This is the reason why really simplicial sense is a real combinatorial way to describe topological spaces and to preserve the homotopy theory there. Okay. Also, it's take here. One of them take fibration to fibration. We'll talk about this when we talk about model category. But what I wanted to say is that here there is more than this adjunction. Okay. Okay. So let's move to homotopy theory. Let's move to homotopy theory because this is what we want to talk about. Maybe before moving to homotopy theory, let me say something about the construction of the in simplicial sets. Like another thing that we will need also later for describe some model of the infinity category, that here the product of simplicial sets is easy. Like this idea of degeneracy makes the product easy because the product of two simplicial sets, like if I have simplicial sets and another simplicial set, so the product will be in the end stage is just xn yn. Like I product something from here and something from here. Okay, what happened? Like, okay, if I have one simplex, or one simplex and like three simplex, the product of them have to give me four simplex, right? We imagine like this, like I have H and a triangle, I product this, give me something from more dimension, but this, because there is the degeneracy, this is what happened. Like the degeneracy make it easy, the product, because I have representative here for everything's down. Okay, so this makes the product, and also the co-limit and the limit, it's easy in general in simply, like just in sets, like it's level wise. Okay, limit and co-limits is level wise. It's so easy in simplicial sets. So this is one of the advantage of simplicial sets. Now the other things I want to move, I don't have too much time, maybe 15 minutes, so I want to move to homotopy theory. In simplicial sets. So first of all, let's talk about co-fibration and fibration. This is also one of the advantages about in terms of co-fibration. So co-fibrations in topological spaces, like it's a good inclusion, like it's an inclusion that it's locally like seem like for example, this the circle in the disk. It's very good inclusion because actually locally we have, it's look like I include this something in cylinder locally. It's look like this, like I have some in the neighbors, I have cylinder for every point, yeah. But the modern way to describe this is these things, like if I have into now I'm talking about topological spaces, and then we move to see what is the corresponding notation for simplicial sets. So for topological spaces, actually to describe in modern way, people describe it this way, like by something here, here this xy, it's a fibration. Actually, if we have here, what is it? I, here I mean 0, I already use this 0, 1 in many ways. Okay. Set. If for every such a diagram, we can lift this. Like if I have this diagram, like what I have here, actually, I have y to z, here is a map, let's call it f. So I have a map from y to z, and I have a homotopy for this map. This is a homotopy here. Like this homotopy actually described by Bethis, like I have for every, but sorry, the homotopy for x, like inside y, this is y, inside this, there is x, and I have homotopy, like every, here, the map, like this is f, but this is f on x, so f on x, I have homotopy for this, like at the beginning it's f, it's exactly the f on x, but there is of course a path. And what it tells, the lifting tell us that we can extend this, okay? We can extend this homotopy, like extension for this map, that give me for every one of x, it's give me a path to all y, okay? This is a modern way to describe cofibration, but it's turned out that cofibration, every inclusion, we mean like injective map, like injective level wise, okay? Inclusion in simplicial set is a good inclusion. It's a cofibration. Okay, every inclusion, it's a cofibration. Like I mean here, like f from x to y, such that all of this fn x is injective. It's a, yeah, it's injective. Okay, this is good. Now, what about fibration? So fibration actually is something that, like the homotopy sense of covering of fiber bundle, but the way to describe this, the modern way to describe
sorry,
this,
Aziz.
like, yes.
The question, I don't see, I mean, how did you get that every inclusion in simplicial sets is
No,
a
I didn't get,
cofibration?
people get, no, when people try to describe the model category for simplicial, sorry, for simplicial sets, it's got that every inclusion, it's a cofibration. Like you have this, like in terms of lifting, like you can lift if you have here inclusion, so you can lift if you have here weak equivalence fibration. Yeah, they define weak equivalence fibration. I will talk now about fibration in the simplicial sets. So you can always lift. You need just here, you need this to be inclusion. You don't need anything else. Yeah, and but why one can imagine this? Because it's level wise, like inclusion, it's very good because we are, yeah, in the inclusion we don't do anything if all of this is injective. So we, like, it's a good, it will be good inclusion because the map is level wise. Yeah, this may be the reason for this, the hidden reason for this, but the definition of this, if you have just squares, this is a can fibration, weak equivalence can fibration. So every inclusion here, and you can lift. It's okay.
Yeah, I mean, okay, I know what is a cofibration, and I suppose that this is how we define model structure, but I don't understand this connection with topological spaces.
No. What I say, like what I want to say here is that the model category of the model category of simplicial sets is different, okay, but it's have some advantage in terms of cofibrations, that everything is a cofibration. This is what I wanted to say. Like, but
okay.
Yeah. Maybe you have to start with can fibration. Yeah. Or for example, in topological space, everything is fibrant, but in simplicial sets, everything is cofibrant, right?
Okay.
Like this, yeah. But in fibration, in terms of fibration, like every inclusion here, it's so easy. Like in topological spaces, both of them, it's not easy, right? The fibration and the cofibration. But in simplicial sets, at least the fibration is easy. Yeah, it's just inject. Okay. So for the cofibration, we define it in this way. The fibration, in topological spaces, something is fibration, something I don't know how to call it, it's like x to y, something pi, let's call it. Something is vibration if has a lifting for this, okay, not z here. Okay, this is the dual for this. Okay, if I have here homotopy, so I can homotopy. Now this is in topological spaces, but now if we want some good notation for simplicial sets, this is what people found, not me. It's too long time ago, that we have to do this with these things, like with the horn. Okay, like instead of this, we take every horn, like it's have to lift with every horn in order to be in simplicial sets. Like something here, it's fibration. If for every, what I mean by the horn, it's like if I have a triangle here, 0, 1, 2. So the horn is just by removing this edge and take just this 2 edge, removing everything in front of this, like, okay, in pyramid, like by removing like the horn in front of this. This is okay, tell us in front of what? So just this and this 3 faces, just, yeah. Okay, this is the horn. So we have here inclusion. So it's the same, like we see, like we fill the horn, like it's something like this, but it's not good to take this. It's good to take these things. This is what people found, and this will be the definition of vibration. If something, it's called can vibration. Pi, it's called can vibration. If it's this thing is lifting, okay. Yeah, this is the definition of can vibration. So,
and in this case, you need unique lifting, right?
What?
In this case, you need unique lifting, so there is only one lifting possible.
No.
No?
No. Can vibration? No. You have just lifting. No. This is a
okay. Sorry. In quasi categories, you have this.
Yeah. The nerve, actually, if you take the nerve, it's not always, but if you take the nerve of the group, it will become vibration. Actually, what is the nerve of a group? Maybe I didn't mention, but group one can think as a category with one object. So there is a nerve of a group. So for the nerve of group, yeah, it will be can. If for groupoid, it will be can, but then there is unique, right? There is a unique, yeah, right. So, okay, it's but this is what happened. Like here, actually, in what I want to say that from here, actually, we get, because I don't have much time. Actually, in topological spaces, actually, if we think a little bit, everything is like if I have this, then everything here, if I have point here, then everything actually we can extend here, no problem. We can extend by repeating ourselves. Here we can't do this always if I have point here, okay? So if something called can complex, X called can complex, if it's fibrant, like we will talk about these fibrant things, if it's have this, so okay, I can put here point, I cannot put here point, but it's like to say that the map to a point, this unique map, it's a can fibration, okay? If we can extend here, actually, we can extend here. This will called can complex, and can complex play, if we can do homotopy theory, good homotopy theory without using can complex. Like for example, if we define the homotopy between two maps to be homotopic, like we can define in the same way, like we have a product, so we product with this with delta 1. If we have like two maps here, X, Y, it's homotopic, okay? If we have this map, some map from here, in simplicial sets, I mean, in simplicial sets. If we have this map such that one inclusion, there is two inclusion here, I didn't describe this, but one can see this, that one of them give me F, one of them give me G. This definition in topological spaces is good definition. It's this definition actually is equivalence relation, but here it's not equivalence relation. We need Y to be can complex. Okay, we will see this more when we talk in general about model categories, how we build the homotopy category. We will see this in more general and in more details. What I want to say at the end, actually, I don't have the time to speak about these things, but at least I can say that singular, like we say that, okay, let's see, this is the last thing. Like we say that if we move by realization from topological space to simplicial sets, by realization from simplicial sets to topological space, we get CW complexes here, right? If I have X, so I get CW complex. And now by moving by this singular, if we move from topological spaces to simplicial sets, actually we get the can complex, okay? The singular, this singular of topological space is a can complex. How we can see this? Because this is the things about the topological space. Like if I have something like this, this is a singular, and I can lift because we can move, because we have the adjunction, we can move to this, right? It's enough to prove that we have here, we have extension here. If I prove that I have extension here, that I have extension here, and here it's easy because actually we have this map, this same map from delta n to this. So we have these maps, like for example, triangle to this. Like we have a section for this, okay? And then we can like this, and this is F, for example. So we can apply this pi, we can put here pi F. Yeah, and back here by the adjunction. Okay, so we see that in topological space because of the continuous we have, but here we work just in combinatorical way. Okay, we work just in combinatorical. We don't have everything still. Even we added the genericity and things, but still we are allowed us to build things with this simplex and okay, one simplex and by degree. This combinatorical way not allow us to everything to lift, but in the topological space we can lift always these things, no problem. Okay, that's why in topological space everything is fibrant, but in in simplicial sets, not, and we need it to build a good homotopy theory. We need this. We need this also for topological space, but we didn't feel before because everything is vibrant naturally. Okay, that is, I think, yeah, it's 1 hour and a half. Yeah. Sorry.
Okay.
Thank you.
Thank you very much, Aziz.
Yeah, thank you. Thank you.
Just a short comment. You should also say what is a weak equivalence. You have.
Yeah, yeah. Yeah. Let me say this. So weak equivalence between x, I, y. If the realization is weak equivalence, okay, we can define this. This okay. If the realization is weak equivalence in terms of topological space. Okay.
Okay. Thank you. Okay.
Yeah.
So thank you very much. Are there any questions?
Thank you.
Okay, it seems that there are no questions, no comments. So thank you very much, Aziz, once again.
Thank you.
We can stop recording. So thank you.